Welcome back. So where did we leave off? We left off where we solved for an over-constrained system of linear equations, more constraints than unknowns, but with a simplified model. So we did y equals ax, only slope was unknown, but the intercept was known. And we did y equals b, intercept was unknown, slope was known. And now we're going to put all those pieces together and solve for the full model y equals ax plus b or y equals mx plus b. And to do that, we need a little bit more machinery, but we're going to start in the exact same way. So let me remind you where we are. We have a bunch of data. They do not exactly fit our model. In this case, that model happens to be a line, but it could be anything. And so our job is not to just ignore a bunch of data and only build a constraint system. We want to use all the data. There's obviously value in all this data. And so what we're going to do is we specify the model, y equals mx plus b. Each point subscripted on I satisfies more or less this equation with a little bit of slop. So really I should have like a plus some amount of noise or perturbation, but I've left off that formality. And the way we've done that is we are going to specify an objective function to minimize. Let me remind you that the objective function we chose, the least squares objective function, is to take the vertical distance between the data and the model, sum the square of all of those, and find the parameters, now slope and intercept, that minimize that overall error. So let me remind you what the vertical distance is. All right, so that point, the vertical distance is just y sub I. The corresponding point on the line is what would happen if I took that point's x-coordinate, shoved it into the equation of the line. I'd get a new value of y, and the difference between those two is my vertical distance. So it's simply mxi plus b, where xi is that point's x-coordinate. So that is where would the y land if it satisfied the line, minus the actual y, that vertical distance. And of course, again, we don't care about a positive or a negative vertical distance. So we are going to square it, and then we're going to sum over all the data points here, and we want to drive that error to a minimum. Now notice, that error won't be zero. I can guarantee it because all of these are non-zero errors. We just want to minimize it. We want to find the line that minimizes the average squared vertical distance between every point and the line. And again, is that the right objective function? I don't know. It's the right objective function for least squares because that's the definition, but there's other objective functions. And we won't get to those in this class, but you should know that this is a choice we've made. And again, we've made that choice because it leads to a particularly clean and closed form analytic solution for the model parameters when you have a model that's linear in the unknowns. All right, so how do we do this? Well, how did we do it before? So when we had just the slope or just the intercept, we just started unpacking this quadratic and the sum, and we started getting all the values out, and then we tried to see how to solve. Well, let's follow the same path here. All right, so we want to minimize that. Again, m and b are the unknowns. You can see that they're not subscripted on the index, whereas x and y are. And now let's start unpacking. Okay, so I have a square of this whole thing. mxi plus b minus yi times mxi plus b minus yi. So I've unpacked that. And now let me just play this out. Now there's three terms in this polynomial, so we have to just be a little bit careful that we get everything. So let me do that step by step. I have this term times this term. That gives me m squared xi squared. I have this mxi times this b, and I have this b times this mxi. Those are obviously the same term, so I have a 2m bxi. I have this b times this b, that's my b squared term. I have 2 mxi's times yi, mxi times yi. Those, of course, both have a negative, so I have a 2 there. We're almost done. We have a b times a yi. We have a b times a yi. Both of those, of course, are negative again, so I have a 2 times that. And then my final yi squared. So what did I do? I just did this in a slightly different order. I did this term times this term times this term times this term. And then this term times this term, this term, this term, and so on and so forth. So it's the same as if you had two terms. You've got to do all three of them. And a couple of them pair up because, of course, they're the same. So that's doubled, and that's doubled. And then these are the square terms. Okay, so just a little bit of algebra, no problem at all. And notice that this is all still within the summation. So all of these indexing on I, still we have to remember that we've got this summation out here. All right, so what do we want to do now? we would like to find the m and the b that minimizes this quadratic error function, which we just expanded out a little bit. So notice now that my error function is two-dimensional. Why? Well, I have two unknowns. So before I was only doing slope and I was only doing intercept, but now I have two parameters that I have to minimize over. Okay, so that's a little bit more complicated. It's going to turn out it's actually not as complicated as it looks. All right, so how do we do that? Well, first let's figure out what is this thing. I mean, I see a bunch of square things, I see a bunch of products, and I don't think it'll surprise you to learn that this is a paraboloid. It is a two-dimensional parabola. And the way you can see that is I have an x squared term here and a y squared term here. I have a linear term here and here, the cross term xy, and then a constant. And this is the form of a paraboloid. The sum, of course, is irrelevant here because I'm just summing all these terms up. So all that happens is there's some scalar here, and so on and so forth. And in fact, I get a paraboloid. Just like in the 1D case where I had a parabola, we have to worry about whether the paraboloid looks like this, upside down, or right side up. This, of course, is the one we want because we're trying to minimize, we're trying to find the parameter. By the way, what are the two parameters here? You know this is a mesh. Well, in one dimension, I'm moving in m, the slope. In the other dimension, I'm moving in b, the intercept. And for each possible value of m or b, I have some value of the quadratic error function. So the quadratic error function, this is just the surface plot, is pick any value of m and b and find the value that's associated with it. And now I'm looking for the m and b that gives me that minimum right there. And in the same way with the parabola, the squared terms dictate what the orientation is. This, of course, is m squared. That must be positive because it's squared. That term is positive. And so, in fact, this parabola, which is the quadratic error function we're trying to minimize, is the type of paraboloid where we can now take the minimum. So now our job is to find the m and the b that minimizes it. Okay, how did we do this before? Well, we had a parabola, and we said, okay, look, the parabola is going to have the property that the derivative, the tangent, is 0 at the bottom. Okay, that's sort of what we have here too, but now it's a tangent not line, but a tangent plane. So imagine taking a small plane and making it tangent to the surface at each point. So as I move down here, that tangent plane will eventually be flat. So think about that parabolic bowl sitting on a table. That little table, that little planar patch is tangent to the bottom, and that's what we are looking for. So what's the definition of that? Well, now we just need a couple of derivatives. So again, that's the point we're looking for. And what we are going to look for is now not the derivative of this, but what is called the gradient. And all I mean by that is that the partial derivative of the error function with respect to m is 0, and the partial derivative of the error function with respect to b is 0. So these are just still two derivatives. They're partial derivatives because that's a function of two parameters. And all I'm saying is that when I move in one direction, the derivative is 0. When I move in the other direction, the derivative is 0, and that of course corresponds to where I have a planar surface that is tangent to the minimum, and that's I have the minimum. So that's the good news. The good news is I can still solve this analytically by, we hope we have to still do it, by just computing these derivatives, setting equal to 0, and solving for m and b. So it's basically the same problem as in 1D. I just got to lug around a couple of derivatives and I have a little bit of more work downstream to do. So the good news is that the generalization to 2D, solving for the slope and the intercept, seems to work out. The bad news is we've got to do a little bit more work in computing the derivatives and the gradients. So when we come back, we're going to do that, and then we're going to see what the solution looks like in a little bit. All right, see you in a bit.